Welcome to Chapter 6, Metabolism. I put in parentheses here and energy because when it comes down to it, metabolism is all about making and using energy. This is the first lesson from Chapter 6. So all of life is energy dependent. And each of the characteristics of living systems, which we have talked about before, metabolism, reproduction, growth and development, homeostasis, requires a constant supply of energy. The interaction of living systems, in fact, is merely an exchange of energy. I love this image here because here we see this carnivore, this apex predator, feeding on this herbivore, this giraffe, and this image encompasses everything that this chapter is all about. So we have the grass back here, which receives its energy from the sun. The giraffe feeds, among other things, upon this grass. That's where the giraffe, the herbivore, gets its energy. And then the lion feeds upon the herbivore. The lion is a carnivore, obviously, feeding upon the herbivore, and it's from there that the lion gets its energy. So if you think about what's going on here, everything in this very simple food chain ultimately receives its energy from the sun. We'll talk about that and the degree of energy that passes from one level to the next as we get into this chapter. Alright, so the objectives of this chapter are to find energy and differentiate potential, kinetic, free, and activation energy. There's a lot going on here in this chapter. Describe the flow of energy in living systems. State the two laws of thermodynamics. Define ATP, that's adenosine triphosphate, which you already know a little bit about. Describe its usefulness to living systems. Define enzyme, which you also know a little bit about at this point. And describe their usefulness in biochemical reactions. And define metabolism and describe its purpose with regard to cell function. Now you've seen this image before of this little person up here getting ready to push this boulder or this large ball down the hill. Now while this ball sits on top of the hill, it is full of potential energy. Remember, potential energy is stored energy. Once the ball is rolled over the edge and gravity takes over and the ball rolls down the hill, now we have energy in motion. We call that kinetic energy. While the ball sits on top of the hill, it can potentially do something, do some kind of work. As it's rolling downhill, releasing its energy in motion, it can then do work. You can roll over a car, a line of people. It's energy in motion, okay? And once it gets to the bottom of the hill and it stops, then we're back to zero. No potential, no kinetic. Okay, so here's a quick check. And my thought for you here is the energy stored in the pyrophosphate bonds of ATP, adenosine triphosphate, is what kind of energy? I'll let you think about that for a second. Your choices are kinetic energy, free energy, potential energy, and Gibbs energy. Okay, so remember that we're talking about stored energy, right? Stored energy, and any kind of energy that is stored is potential energy. It is energy that can potentially do work or be used to do work. So if you answered potential, you're absolutely correct. So recall, you've seen this illustration before as well. As electrons move away from the nucleus, here's the nucleus of an atom. As electrons move from one energy shell to the next, away from the nucleus, their potential energy increases so that an electron way out here in the outer shell can potentially do a lot of work. There's a lot of power stored in that electron, and it can interact with the electrons of an adjacent atom and form a molecule. Okay. By the same token, the reverse is true. As electrons move from energy shell down closer to the nucleus, and it's not really an up-down. This illustration merely illustrates that as you get closer to the nucleus, the potential energy of that electron goes down or decreases. And that idea will be forever important for you to remember as you study biology. Okay, thermodynamics. So thermodynamics merely pertains to heat exchanges. There's whole classes in physics and on thermodynamics, and we're not interested in all of the details of thermodynamics, but we are interested in the first and second laws of thermodynamics because they play important parts in organic systems. So energy is mechanical, heat, or can be mechanical energy, heat energy, like from the sun, sound energy, electric energy, light, radioactivity is also energy. Energy is measured in units of heat because all other forms of energy, mechanical, sound, electric, light, etc., can be converted to heat. So thermodynamics pertains to heat exchanges, and we have two laws to concern ourselves with. The first law of thermodynamics states that energy is neither created nor destroyed. It merely changes form. So we do not make energy. We cannot break energy. It just changes form, like from the sun to the grass to the giraffe to the lion. It's going from source to source. It changes sources or changes form, but we never create it or never destroy it. Heat is measured in kilocalories. Energy is measured in units of heat. That is the kilocalorie. Kilo means 1,000, so 1,000 calories. That's the KCAL or lowercase KCAL. 1 kilocalorie is 1,000 calories. Now, 1 calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. So it's a 1-1-1 proposition here. 1 calorie, the amount of heat required, because remember, energy is measured in heat units, and 1 heat unit is a calorie. So 1 calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. So it's a 1-1-1 proposition. So ecosystems get their energy from the sun. Ultimately, all energy comes from the sun at the rate of 40 million billion calories per second. Now, plants and algae and some bacteria conduct photosynthesis, and I think you're familiar with that term from 10th grade biology or 7th grade life science. That photosynthesis is where light is absorbed from the energy and turned into chemical energy. And that's what photosynthesis is. Synthesis, we're synthesizing something using photo, which pertains to light. So photosynthesis converts light energy from the sun into chemical energy. And light energy is stored as potential energy in the covalent bonds of glucose. And we'll see that process, especially as we get into cellular respiration. So remember redox reactions? Redox reactions transfer electrons from one molecule to another. It's a combination, or it's the pair of reduction and oxidation reactions. Remember, we don't have a reduction reaction in an organic system without an accompanying oxidation reaction. So what happens here in a reduction reaction, remember that a molecule gains an electron. It gains an electron, so it becomes more negative or less positive. It's reduced from a more positive position to a more negative position. It gets reduced. Its electrical charge gets reduced. Whereas with an oxidation reaction, a molecule loses an electron and therefore becomes more positive. So reduction increases the potential energy, right? Because if we gain an electron and become more negative, right? We're gaining an electron, and so now we have an extra electron now that can interact with another molecule in the milieu, right? So it becomes more potentially reactive, increases potential energy. And so here we see that in this little diagram here, where A loses an electron and becomes a more positive, thereby being oxidized, and B gains an electron, therefore becoming more negative, and is thus reduced. Now, thermodynamics, again, the total amount of energy in the universe is constant. So again, you don't make energy, we do not make energy, we do not destroy energy, it simply changes form. The first law of thermodynamics, as we've said already, energy is neither created nor destroyed, it merely changes form. And the energy in living systems, you know this now, is stored in chemical bonds. So energy flows only in one direction, that is from the sun to the grass, to the giraffe, to the lion. As living systems do work, only a fraction of the energy is used. Most of that energy is released as heat. Think about it when you exercise. When you exercise, you're running or walking on the treadmill or doing aerobics or whatever. That uses a lot of energy, obviously, but what happens in the process? You begin to perspire, you sweat a lot, you get hot, you sweat a lot, you have to drink water. That is energy being released as heat. And interestingly, only a small fraction of the energy that you take in gets used for the exercise. Most of it is released as heat. Okay, so the second law of thermodynamics, or first law, energy neither created nor destroyed. Second law of thermodynamics, as energy in a system we're talking about decreases, the degree of disorder increases. And disorder we refer to as entropy. Entropy. All right, so as energy decreases, in other words, as you work, as you do the exercise, the degree of disorder, entropy, increases. And think about it with regard to the exercise illustration that I just used, right? You're running on the treadmill or you're running a marathon, you're using a lot of energy, you build up a lot of heat, you start to perspire. And what happens? You get tired, your muscles get sore, you get winded, you get hot. That's entropy. All right. When you go from beyond your homeostatic balance, that is, you get hot, you get tired, your muscles get sore, you get winded, it's hard to breathe. That's disorder, right? When everything is in order, when you're in homeostatic balance, you're calm, cool, and collected, you're breathing easy, you're relaxed, you feel good, there's no aches and pains. But when you go run the marathon, you start to have aches and pains, and you get tired, and your muscles get sore. Okay, that's disorder, that's entropy. So think about it like this. Entropy is the amount of disorder or randomness in a system. So ice, we're talking about water, right? Ice, the solid form of water, represents the maximum order with regard to water, right? The maximum degree of order. You can't go anywhere. If you're ice, right? Ice is solid, there it is, immovable. Water, then, liquid water, is the maximum degree of disorder. And so as ice here in this glass starts to melt, right? This is solid ice, maximum order. As it starts to melt, the degree of disorder increases. And if liquid water is the maximum degree of disorder, then in this glass we have the highest amount of disorder, or the highest amount of entropy. So the point here in this illustration is that entropy, the amount of randomness or disorder, increases as ice melts. And it makes sense. The water molecules here in this glass can interact with one another. They're flowing freely around. The molecules, as you've seen in the illustration from one of the other chapters, in the water molecules in solid ice go nowhere, right? They form this nice geometric shape, and they go nowhere. They're crystalline, and they're immovable. However, once they start to melt, then the water molecules are released, and they can flow around and interact. That's randomness. That's entropy. All right, here's another quick check. Here's the statement. As the energy of a system decreases, the blank in the system increases. All right. Think about what we just talked about. Your choices are entropy, order, enthalpy, potential. So as the energy of a system decreases, what in the system increases, right? Remember, energy, potential energy, is maximum order. We call that, by the way, enthalpy. So if you answered entropy, then you are correct. So as the system becomes more random, as energy is released from the system, things become more random, entropy increases. Okay, so remember that chemical bonds increase order, right? When things are bound together, they're solid, immovable. I mean, they're not really immovable, right? But the idea here is they're fixed for at least a certain amount of time. So order is increased. Heat increases disorder. So when you heat something up, when you boil water, disorder. When you melt ice, disorder. When you go out and exercise in the hot sun, disorder. Living systems are always in flux between order and disorder. Order, by the way, is that enthalpy term that I used before. Entropy, enthalpy. It's back and forth. Order, disorder. Enthalpy, entropy. We have another term for energy. It's called free energy. We also refer to this as Gibbs free energy, named after the person who first described this type of energy. We generally just refer to it as free energy. It's a total amount of energy in a system now available for doing work. It's obvious, it's frequently abbreviated delta or delta G. That stands for the change in energy, or the change, delta G, change in Gibbs free energy. Okay? Or in other words, if you see delta G, we're referring to free energy. That's the amount of energy available for doing work. So biochemical reactions change the free energy, obviously, right? Because you have energy in chemical bonds, like the pyrophosphate bonds of ATP. You break the bond, you break the bond, that releases energy, which then can be used to do work. So reactions with regard to energy and the release of energy and the absorption of energy, reactions may be endergonic or exergonic. Now look at this. Endergonic reactions require the addition of energy. We have to input energy into the system. That's the ender part. Ender, think about ender or indo or inside, right? These are reactions that require an input of energy. We have to add energy to the system. They therefore cannot happen spontaneously. Okay, so your car just doesn't start moving on its own. You have to turn that thing on, you have to get the pistons firing, you have to start the gas burning, and then you can do work. Then you can drive the car. So you have to do something. You have to input energy to the system. Versus exergonic. Exer or exo means an output, or to put out of, or outside of. So exergonic reactions release energy. So when the reaction happens, energy is released. For an endergonic reaction, you have to add energy to do the work, to make the reaction occur. Exergonic reactions, when they happen, they release energy. And so therefore they may happen spontaneously. That'll make more sense in a second. So endergonic reactions, a nice illustration here. Energy of the products here, products, is greater than the energy of the reactants here. So this is Gibbs free energy. So the energy of the products, remember, we add the reactants together and we make the products. That's the reaction. The energy of the products is greater than the energy of the reactants. So look at it this way. In order to go from here, this is the energy level of the reactants, to up here, right? This is like climbing a hill. We have to move up. So the reaction, we say, is uphill, right? We're going from here to there, so we have to go uphill. So the energy must be added for the reaction to proceed. The delta G, or the change in Gibbs free energy, is greater than 0. Delta G greater than 0, which means that energy must be added to the system to cause the reaction to proceed. We must put energy into the system. That's the endergonic part. That's the ender part of endergonic. Okay, it's an uphill reaction. Versus the exergonic reaction. Here, the energy of the products, way down here, is less than the energy of the reactants. So this is like the person standing at the top of the hill with the boulder or the big ball and rolling the ball downhill. So we say the reaction is downhill, because once you cross the threshold, the reaction occurs spontaneously. It automatically happens. It's like gravity pulling the ball down the hill, right? You push the ball over the edge, gravity takes a hold. You can't stop the ball. You can't stop the snowball from rolling down the hill. It happens automatically. So, in other words, energy is released as the reaction proceeds, right? We have lots of potential energy here. Once you go over the edge, over the threshold, the energy automatically happens, and the energy therefore is being released from the system. Lots of potential energy here. We have energy in motion as the reaction proceeds and we make these products. And it happens automatically. We don't have to do anything to it. So the change in Gibbs free energy is less than zero. No energy is required to cause a reaction to proceed. It happens automatically because the energy of the products is much, much less than the energy of the reactants. It's a downhill scenario here. So here's a little chart that may help you remember endergonic versus exergonic reactions. Okay, endergonic reactions have a positive delta G. Remember that's Gibbs free energy. Exergonic reactions have a negative delta G. Endergonic reactions, we have to add energy to the system, which means they're uphill direction of the reaction, and exergonic reactions, they happen spontaneously, which means they're downhill. Energy in endergonic reactions must be supplied. That's the ender or endo part. With regard to the exergonic reactions, energy is released. That's the exer or exo part. And endergonic reactions are obviously not spontaneous because they're uphill, whereas exergonic reactions are spontaneous because they're downhill. Here's a quick check. Reactions that proceed spontaneously, where the delta G, Gibbs free energy, is less than zero. That means the energy of the reactants is much less than the energy of the products. We call those what kind of reactions? Your choices are endergonic, catalyzed reactions, explosive reactions, or exergonic reactions. Well, they proceed spontaneously. We do not have to add energy to the system. As the reaction proceeds, energy is released, is let out of the system. That's obviously the exergonic scenario. Finally, we have the activation energy. Now, activation energy, think about the terminology here. It's energy required to activate something. And what are we talking about? In biochemical systems, we're talking about biochemical reactions. So it's energy that is necessary to begin a biochemical reaction. Remember the exergonic scenario, right? Requires an input of energy. What kind of energy is that? That's your activation energy. So it's the amount of energy needed to start a biochemical reaction. And here's a thought for you. If you ate something and you didn't have some way to speed up your reactions, right? To digest the hamburger that you had for lunch, for example, it would take you millions of years to break down that hamburger and extract the energy from it so that you could then in turn turn around and go run your marathon. It would take millions of years, literally. It would take so long that you would be dead long before that hamburger was processed and you could extract the energy. So, in biochemical systems, we have these things called catalysts. Catalysts are substances added to a system to lower the activation energy. So in other words, to make the metabolism, or rather the catabolism of that hamburger occur, you need to add energy. It doesn't happen spontaneously. That energy is activation. However, in the normal scenario, you're adding the energy, the energy to cause the catabolism of the hamburger to occur, to be activated. It is such a slow process that it would take you millions of years to digest and catabolize that hamburger. So, biochemical reactions make use of these substances called catalysts. They are proteins. We'll talk more about catalysts by way of enzymes in the next lesson. But these are substances that add to a system to lower the activation energy. So instead of taking 1,000,000 years to digest and process your hamburger, now it takes only a couple of hours. So here is your little graph here with Gibbs free energy on this side, course of the reaction going to the right here. So in an uncatalyzed reaction, that's the little blue line here, we start out at this level, whatever it is, and we don't really care what this number is at this point to digest your hamburger. The energy, we have to add energy to the system because it's endergonic, and eventually we'll get to the point where the reaction can occur and we can digest the hamburger. That point, or the amount of energy that you must add to get to that point, is called the activation energy. All right. Now, this is going to take a very, very long time to get up to this point so that the reaction can proceed. It takes a long time. So, in order to decrease the amount of time so that that reaction occurs quicker, faster, in a shorter period of time, we add a catalyst. And when we add a catalyst, it takes the activation energy from here to there. It doesn't seem like a lot on this graph, but in biochemical systems, it's a lot. We're talking about millions of years, right? So we're reducing the activation energy. Remember, that's the amount of energy required to make the reaction proceed. We're taking it from here to there. And when we do that, that reaction now proceeds quickly, and that hamburger gets digested, broken down and digested in a matter of hours rather than a matter of millions of years. Here's the activation energy with the catalyst present. Here's the activation energy without a catalyst. You can see the difference, okay? So a catalyst decreases the activation energy, or the amount of energy required to make the reaction proceed. Okay, so what is all this talk about energy about? It's about ATP, adenosine triphosphate. Remember, this is the energy currency of the cell, and I've used that phrase before, and it's something that you want to remember. ATP is 3 phosphate groups, and you know a phosphate group as a phosphorus molecule, that's the P, with 4 oxygens attached. And it's 3 of these phosphate groups attached together in tandem to adenine by way of ribose. And again, ATP, adenosine triphosphate, and you want to remember this forever, is the energy currency of the cell. Now, ATP occurs in a cycle within the organic system, within your body, for instance. Okay, you do not make a whole lot of energy at any one time. You do not store a whole lot of energy at any one time. However, you constantly need energy to survive, to live. Even when you're sleeping, you need energy. So where does all that energy come from? Well, your body has a great program of recycling energy, and here's how that works. It's called the ATP cycle. Here's ATP, obviously described or obviously represented as this like sunburst or this burst of light representing energy. Energy, that's ATP. And remember, you have a high amount of potential energy conserved in the pyrophosphate bonds of ATP. Those are the bonds that connect one phosphate group to the next phosphate group to the next phosphate group. Okay, those are pyrophosphate bonds. Lots of potential energy stored in those bonds. How do we break covalent bonds? I'll give you a second. Hydrolysis, hydrolysis. We lyse the bonds by adding water. So we take ATP, a molecule of ATP. We add a molecule of water. We break the pyrophosphate, the terminal pyrophosphate bond, the last one, or the first one, however you want to look at it. It's the furthest one away from the adenosine. We break that bond by adding water, and we release energy. This is energy for endergonic cellular processes, or this is your endergonic reaction, or this is the energy release so that you can drive an endergonic reaction, a reaction that requires energy. For instance, for example, active transport. Remember we talked about active transport. That requires an input of energy. Where does that energy come from? ATP. Active transport is an endergonic reaction. It's moving substances from an area of low concentration to an area of high concentration. It's pushing yourself into that crowded room. Takes energy, takes effort. Where does that energy come from? ATP. That's an endergonic reaction. Then that free phosphate, here you see it here, is recycled in the milieu. Now, when you take off, this is ATP, adenosine triphosphate. When you take off one phosphate, then you have the phosphate with, then you have the adenosine with two phosphates connected. We call that now ADP, adenosine diphosphate. If you take off another phosphate, then you have AMP, adenosine monophosphate. Okay, so once you remove the phosphate group by adding water to break the pyrophosphate bond, then you turn this into ADP, adenosine diphosphate. That remains in the milieu, and the phosphate now, which is free-flowing, once the endergonic reaction or endergonic process occurs, then that phosphate, that free phosphate, can recirculate, reattach to ADP to make a new molecule of ATP. So we use the energy in the pyrophosphate bond by driving an endergonic reaction, and then through the synthesis process, we form ATP by reconnecting that pyrophosphate bond, right? And we turn ADP back into ATP. This is energy derived from exergonic cellular processes. All right, we call this the ATP cycle. It's ATP, we break a bond by adding water. We use the energy from the phosphate to drive an endergonic reaction. The phosphate then gets reattached to ADP to make ATP, and that energy then can then be used to drive another endergonic reaction. So we have this circle, and that's how your body always has a supply of energy. Right? We don't make a lot at one time. We don't store a lot at one time, but we always have this cycle going on. So we're always conserving. We conserve energy, right? We break it down, we use it, put it back together, right? We have this cycle going on all the time. All right, so the pyrophosphate bonds are high energy bonds. Hydrolyzing the terminal bond releases energy, which may then be coupled to a reaction, an endergonic reaction, to do work like active transport. Here's the reaction that you're familiar with. Here's ATP, add a water to it, turns to ADP, releases that terminal phosphate. That energy can be used to drive an endergonic reaction, and then, according to the cycle, the phosphate group is reattached to ADP, and we're back to ATP. Phosphate group is attached to ADP with a concurrent release of water. We're back to ATP. That's why this arrow goes both ways. So the energy here, when you break ATP, is used to drive endergonic reactions, and the cells use ATP cyclically, and so therefore we do not store ATP to any degree long term. Obviously, when marathon runners, the night before the race, they go out and they carb load, eat lots of spaghetti and lots of bread and lots of pizza. They're storing fuel which they will then use to make ATP so they can run 26.2 miles. So you store the fuel, but you don't store the energy. Okay, quick check. When the terminal pyrophosphate bond of ATP is blank, energy is released. All right. So we're going to do something to the terminal pyrophosphate bond of ATP to release energy. What are we doing to that bond? That bond is, when that bond is catalyzed, we release energy. Hydrolyzed is one of your choices. Synthesized is one of your choices. And Simonized is one of your choices. Obviously, it's not Simonized. I just threw that in there because I couldn't think of another ized word. All right, so we're going to cleave the terminal phosphate bond. How do you cleave it? Hydrolysis. You add water. Hydrolysis. So if you answered hydrolyze, you're absolutely correct. So now this says let's go to the video, and when I'm teaching this class live, I actually present the video to my students, which I cannot do here, but here is the link. It's a YouTube video called ATP, or adenosine triphosphate. It's a pretty good, simple little, very short video on ATP and how it is used, or how it is tapped to drive inorganic reactions in living systems. I put this link in your little list of things under module 3. So you want to make sure you go and watch that short little video. It's just a couple of minutes long. Finally, this is just kind of a review of exergonic and endergonic reactions to kind of prepare us for going into the next part of Chapter 6. Okay, so here we see the energy of the reactants and the energy of the products. Here we see a very stable molecule consisting of 3 glucose molecules. This is a trisaccharide. Everything is connected together, everything is linked together, everything is bound together with covalent bonds, very ordered. We add energy into the system, we break those bonds, we release those 3 little glucose molecules with the concurrent release of energy. This is the typical exergonic reaction, right? We're releasing energy. Energy is released, it happens spontaneously. Entropy increases. So if you can look at a graph like that or describe a reaction in terms of the amount of energy released, in terms of whether it happens spontaneously, in terms of the amount of entropy, whether entropy increases or decreases, and the idea that the energy of the products is different from the energy of the reactants, then you put the nail in the coffin with regard to exergonic reactions. So here exergonic, we're releasing energy. So here we are forming ATP, right? We're releasing energy. So here we're taking the phosphate, the terminal phosphate, and add it back to ADP to release energy, which is ATP. Now, versus the endergonic reaction. Ender, right? By definition, we have to add energy to there. So here's your ATP. We're going to cleave that terminal phosphate bond. All right, and we need energy to do that. Here are your 3 little glucose monomers. We need to add energy to the system because the energy of the reactants is lower than the energy of the products, so it's an uphill reaction. Once we add energy, then we can form those glycosidic bonds again and make that trisaccharide all over again, so we have to add energy to the system to do that. That's your endergonic reaction. Energy is required, it is not spontaneous, and entropy decreases. We go from a place where we were completely in disorder, in disarray, and we go to a much ordered system with the trisaccharide here. Okay, that is the end of this lesson, the first lesson of chapter 6, and we'll continue.